Hi everyone, my name is Tejas and I'm a software engineer in the Spark team at Facebook. In this talk, I'll be talking about Hive bucketing support in Apache Spark. So this is the high-level agenda of the talk. I'll first describe why we need bucketing, why is shuffle bad, and how do you avoid it. And in the later half, I'll talk about the bucketing support in Spark and how it differs from the Hive bucketing support and the work done so far to have Hive bucketing in Spark. So let's get started. Why do we need bucketing? When we looked at the queries that our users run in production clusters, a good chunk of them are doing joins. And there are three main join implementations that we use. The first join implementation is a broadcast hash join. So in this join, what happens is you are joining two tables and one of the tables is small enough that can fit in memory of the executors. So Spark will ship the small table to all the executors and then this is cached from the executors and the other relation is streamed and the join is done. The second join implementation is shuffle hash join. In this implementation, both the tables are shuffled, and on the reduce side, when the shuffle outputs are gathered, then one of the tables is buffered into the memory, and the other relation, which is a bigger relation, is streamed, and the join is performed. And lastly, there's a sort merge join. So this is used typically when your tables are quite large in size. So the data has to be shuffled, and on the reduce side, it has to be sorted, and then the join is performed over it. Turns out that most of our tables are really large in size. So we end up using sort merge join quite often. So let's look at what happens in a sort merge join. So you have two input tables, table A and table B, and these have been joined using sort merge join. So first step is the mapper are reading the input tables and then they write out the shuffle outputs. Then the reducer reads the shuffle outputs from the map nodes and then the data is sorted and finally the join has been done. So if you look at the Spark UI, this is how this query will be represented. So on the left hand side top you see stage 0 and stage 1 and over there you see whole stage code gen. So that is nothing but scanning the tables and below you can see the output is given to the exchange node. So exchange is the physical operator responsible for doing shuffle in Spark. And once the data is read and shuffled, on the right hand side you can see stage 2. So in stage 2 there's exchange again, so that is reading the shuffle outputs. Later there's whole stage code gen, that is nothing but doing the sorting of the data. And then after the sort outputs are there, the sort merge join has been done and finally the data is written out to the resulting table. We deeply care about the performance of all the queries that your users run in production. And to do so, we look at two important metrics. First, what is the cost of running a given query in our clusters? Second, what is the latency of the query? And to look at these things, we divide the query or measure the cost of the query into multiple phases. So phase can be something like reading the inputs, doing the shuffle, sorting the data, performing the join, and finally writing out the results to the output table. So when we looked at the cost of each one of this individual phase, we found out that shuffle is quite expensive. And why do I say that shuffle is expensive? So let's look at what happens inside a shuffle. So from previous example, you have two tables, table A and table B. And then in the map phase, these input tables are read and the shuffle outputs are written to the disk. So this is a disk write, which is expensive I/O operation. Later, when the user is trying to fetch these outputs, it has to read it from the disk. So again, this triggers a disk I/O operation because it's a disk read. Now, any disk I/O operations are super expensive. Apart from disk I/O, there's network I/O as well. So imagine if there's this query which has mappers and reducers, and you have M mappers and R reducers. In total, there will be M into R network connections. So there is disk I/O, there's network I/O, and I/O in any form is expensive. So how do we avoid this shuffle from happening? So at high level, this is how these queries look like in production. So most of them are reading two tables, performing the shuffle, and then the join, and finally writing the results to the output table. When we look closely at these queries, so say for example, I have the student table. Now the student table is joined with the attendance table. The join key is the student ID. Next query, student table is used again, is joined with the examination results table. This time the key is again student ID. So every time the student table is accessed in a join, what is happening is that you're reading the same student table, you're doing the shuffle on the student ID, and the reduce side, you're reading the shuffle outputs and doing the sort on the student ID, and then performing the join. So if you have to avoid this cost, what one can do is that why not pre-compute this shuffle and then store this in the input tables. And that's what bucketing is. So bucketing allows you to pre-shuffle and sort your inputs based on some keys. So here's how things look like without bucketing. On the left-hand side, I have the job which is populating the student table. Let's assume it's a single-stage job. After the job is done, on the right-hand side, you can see there are queries which are consuming this student table. And each one of them is reading from the same student table, doing a shuffle, and then on the reduce side is reading the shuffle outputs, and doing a sort, and then performing the join. Now, if you switch to a world with bucketing, this is how things look like. So on the left-hand side, in the bottom, you can see that this is the job which is populating the student table. And this has to do shuffle because you have to pre-compute the shuffle and sort. And later on the right-hand side, you can see that all the jobs which are consuming from the student table, they don't have to do shuffle at all. And they are running as a single stage. So the trade-off here is that instead of shuffling over and over again, you can pre-shuffle and sort the data once so that any downstream pipelines which are consuming this table do not have to shuffle, and they run quite faster. So what are the savings that we are talking about? So we did a benchmark for one of the production jobs with and without bucketing, and the blue bar is without bucketing and the yellow one is with bucketing. So as I mentioned earlier, we care about two metrics. One is how much is the cost of running the query, which is represented using the reserved CPU time on the left-hand side. And on the right-hand side, I have the latency of running the query. So you can see in both the axes, bucketing is making a big difference, and the cost of running the query is also lower. So whenever our users see this, they are really happy. They say, hey, why not just use bucketing everywhere? And we figured out some patterns where making use of bucketing makes sense. So the first pattern is kind of the example that I've been using so far in the presentation, wherein you have some set of tables that you're using frequently in joins, and they have some kind of primary key. Classic example is the student table where the primary key is student ID. Another example is employee table with employee ID, and so on. So these tables are typically called as the dim or dimension tables. The other pattern is when you have to do a daily cumulative loading of tables. So say for example, you have a big table, which is a base table which has all the events for your service since day one. And every night you get a delta table which has all the user activities for past 24 hours. So every night there will be a job which gets this base table and the delta table and merges them together to produce a new version of the base table. Now if both the base and the delta table are bucketed, then this merging process will run quite fast. The third pattern is when you want indexing capabilities. So bucketing is not really indexing like in which the traditional database offers. But if you are using bucketing, then let's say if you're looking for a row for a particular student, you can hash on the student ID, find out which bucket the rows belong to, and if you're using sorting, then you can do a binary search on that file and find out the desired row. Now let's switch and look at what is the bucketing support offered in Spark. Spark started supporting bucketing since early 2016, and this was added this was launched with Spark 2.2. And with this support, users could create bucketed tables in two ways. One is using the data frame APIs. So it's simple. You can say data frame.write, and you can specify the bucket columns using bucket by. If you want sorting, you can use the sort by API. The other way is using a SQL statement. So when you create a table, you can use the cluster by and sort by. So cluster by is used to specify the bucketing columns. Sort by is used to specify the sort columns. And finally, you specify how many buckets you want. So after this point, any inserts to this table will ensure that the output is in a proper bucketed form. Now, if someone says that, hey, I've already bucketed this table for you, you can go and check what's the bucketing properties of the table. So to do this, you need to do describe formatted on the table. And in the output, you can see that this example table has 64 buckets, and it's bucketed and sorted on the student ID column. Spark SQL Planner has some optimizations which are tailored for bucketed tables. And so if you want to enable those, set this configuration to 2. So when we moved from Spark 1.6 to 2.0, I was excited to see the bucketing support, and I started playing around it. And so I tried out this example query. Now in this query, there's a join amongst two tables. So there's table A, table B, and the join is over columns I and J. And when I ran this, I saw this physical plan. So by the way you read this physical plan is bottom up. So on the bottom, the first operation done is table scan, then there's exchange, which is basically shuffle, then there's sort, and then finally the sort merge join. So since both the input tables are already bucketed on columns I and j, and that's your join predicate, I was expecting that there shouldn't be any shuffle because the whole point of bucketing was the data is pre-shuffled and sorted. So then the fix that we made was to get this information that the table is bucketed and propagate back to the SQL planner. So after the fix, now this query runs as a single stage job. So there's no more shuffle, it's quite fast. As we are migrating more and more of our workloads from Hive to Spark, we ran across tables which were bucketed. And it happened that when we run the same query in Hive and Spark, the outputs created are different. So for migration, we wanted to ensure that we had complete backward compatibility. So we found out that there is some semantic differences in how Hive bucketing works versus Spark bucketing works. So let's look into that. So when Hive says that a table is bucketed, this is what it looks like. A table has n buckets. Physically, in the storage, that is the SDFS or S3, there will be n distinct files. And every file represents a single bucket. In Spark, if a table has n buckets, it can have more than n files physically. Why is that? So we looked at how these tables are populated in both the engines. So let's look at Hive. In case of Hive, if you want to populate a bucketed table, it has to be a MapReduce job. And if the table has n buckets, then Hive will ensure that the MapReduce job creates and reduces. So each reducer after the shuffle gets the rows for a particular bucket, and then it writes out the rows to a single file. So that file is basically the corresponding bucket. And since you're writing a single file per bucket, Hive can ensure that the bucket as a whole is sorted because it's just a single file. In Spark, when Spark creates bucketed tables, it can do it without using a reducer. So this is quite fast because whenever there's a reducer, that means that you're shuffling the data around. The way this works in Spark is that every single mapper can get rows responsible for multiple buckets. So let's say if Spark mapper sees that, hey, this row corresponds to bucket I, it will create a file for bucket I and write it inside that file. Next up, if it sees that there's a row for bucket J, it will create a new file for bucket J and write it over there. So potentially, every mapper can create n files where n is the number of buckets in the table. So as you can see over there in the bottom, there are multiple files per bucket in the Spark world. And that means that there's no guarantee that the bucket as a whole is globally sorted. So this is kind of a summary of what I talked in the past 2-3 slides. So the model of Hive is that it will pay huge cost when it's producing the Hive bucketed tables, but then whenever you're trying to read it, on the reader side, it will be less expensive because there's a guarantee that the data is globally sorted. In case of Spark, it's opposite. So your writes are cheaper, but whenever you're reading the data, then you have to sort it if you want to do, say, sort merge joins. Unit of bucketing in Hive, it's one file per bucket. In Spark, there's no such guarantee. And sort ordering. So since Hive has one file per bucket, if you sort the file, then you have the global sorting across the bucket. In Spark, there's no such guarantee. And finally, Hive and Spark both use a different hashing function. So whenever there's shuffle happening, in Hive, it uses its own algorithm or hashing function to do the hashing. So the distribution of rows after doing the shuffle is different across both these engines. So since we wanted to migrate our workloads from Hive to Spark, and in a backward compatible manner, we started looking at how do we have the same semantics of Hive bucketing inside Spark. So the goal here was that if you have any Hive query, which is reading from a table and writing output to some Hive table, if you run the same query in Hive and then in Spark, the output should be exactly identical. So this is the master Jira for adding Hive bucketing support in Spark. So, and I'll go over roughly what are these individual tasks. So first is have a Hive compatible hashing function inside Spark. Later on, enable creating bucketed tables, Hive bucketed tables in Spark. That means that if you are bucketing, then you need to store that information in Metastore. And if you are to reading a bucketed table, then you have to read this information back from Metastore. Later on, whenever Hive is querying bucketed tables, it uses a specific file format so that whenever there's split generated, so it knows that this table is bucketed, so each bucket is treated as an individual split. And later on, you need to propagate the constraints about bucketing inside the SQL planner. So the last two items are really some optimizations that could be done. As things stands, the first two tasks are completely merged into open source Spark. And since we had internal business deadlines, I implemented the other two tasks in our own FB private Facebook branch. So this has been in production for past 6 months. It's running stably, and we plan to merge it, contribute it back to open source. So as I was working on this project, I came across some places where the SQL planner could take use of bucketing properties of the table. And so from this point, whatever JIRAs I'll talk about are all merged into open source trunk, except for one of them which is still in review. So here's the first one. Here is a query which is doing a join over two tables, table A and table B. And the join keys are X and Y. And when you run this query, this is the plan created by Spark. So you can see it's a single stage job, there's table scan, and you directly do the join. By the way, I forgot to mention that both the input tables here are bucketed on X and Y. So that's why there's no shuffle. Now, let's say if the user flips the order of join keys. Instead of saying that I join on X and Y, let me join on Y and X. And what happens is, all of a sudden, Spark starts doing exchange and sort. So exchange is basically a shuffle. So this makes no sense, because your table is already, the whole point of bucketing is that you need to have, the data is already shuffled and sorted on X and Y. The fix here was to make sort merge join not look at the ordering of the join predicates in the query string, instead leverage the bucketing properties of the table. So after this fix is done, then this sort and shuffle is eliminated, and this same query runs as a single stage job. And it's much faster. Next up, I have Spark 17271. So over here, there's again a join, and the join keys is column 1, and the tables, both the tables in the join are bucketed on column 1. This is the plan generated by the Spark planner, and you can see that on the bottom there's table scan, and there's sort, and then finally a sort merge join. So again, since both the input tables are bucketed and sorted on column 1, this sort is really not necessary. The bug here is that the query is using alias. As you can see, table 1A join table 2B. So when you use the alias, it confuses the planner. So the planner thinks that the sort merge join says that, hey, I want my children to have the data partitioned on A dot column 1. But it doesn't know that A is nothing but table 1. So the fix here was to do a semantic comparison of the sort ordering. And after the fix is done, the job runs without having the extra sort operation. So by the way, we see that whenever you have sort and you are running with a larger data set, then the sort will have to spill to disk, which is also a disk I/O. There's a disk write and disk read. Next up, I have Spark 17698. So over here, this is the query where I'm doing a join over two tables. It's a full auto join, and so here's the plan created by the Spark SQL planner. So you can see there's a table scan, there's a shuffle exchange, and the sort merge join. The query predicates there are A.id, B.id, and AID is equal to 1, BID is equal to 1. Both the inputs are bucketed on ID. So again, there's no need to do the shuffle and sort, because the tables are bucketed on ID, bucketed and sorted on ID. The bug here was that Spark used to think that the sort merge join operator used to think that I will treat all the three predicates as the join expression. But in reality, only A.id is equal to B.id is the join expression. The other two expression, A.id is equal to 1, B.id is equal to 1 are just filter clauses. So the fix done was to separate out the join expressions from the filter expressions. So after the fix, the same query runs as a single stage job. And there's no more shuffle. So this is more of a scalability fix. We used to often see that our queries are ooming in production whenever they are doing a sort merge join. So let's see why there were ooms. So whenever there is sort merge join, this is what happens underneath. So on the left hand side, you can see there's a buffer. So one of the relation is buffered and the other one is streamed. And the buffering is done only for all the rows corresponding to a key. So imagine if you have account for some celebrity like Taylor Swift, and you're doing the join over all the followers of Taylor Swift. So if you start buffering all the rows for followers of Taylor Swift, that will be huge, and that won't fit in memory. So this buffering will take up a lot of memory, and then you can see a The fix you done was that whenever your buffer hits some threshold, Spark will automatically start spilling the data to the disk. And whenever these rows are again needed, it will read back from the disk. So after this, these queries run reliably. They do not out in production. So finally, this is the summary of my talk. Sort and shuffle are expensive because they involve extra like disk and network I/O. And bucketing can help you to avoid that. If you are using bucketing, you can expect 2 to 5x gains in the performance and latency of the query. And there are some differences in how Hive bucketing works versus Spark bucketing works. And there's ongoing work to make Spark work with Hive bucketing.
We have 2 mics on the either side of the aisle. If you have any questions, please line up. We've got about 9 minutes. I know we're holding you away from lunch, but good question is worth it. Go ahead.
Is it good now? Yeah. So my question is, how do you compute the number of buckets and kind of consequently the number of files to produce? One thing that we're seeing is that the number and size of files is a big factor in performance. So I was wondering about that, like how to decide.
Yeah, so good question. So in terms of how many buckets you want, we try to keep the size of individual buckets to be like say around 1 or 2 gigs. But at the same time, let's say if your table is super large, then you can exceed the number of files that you produce. So at max, what I've seen is 32,000 is the max number of buckets that we use. We don't go beyond that.
Go ahead, ma'am.
Can you talk about bucketing versus partitioning in terms of performance?
So I was expecting that question. Thank you. So with bucketing, say you can have a pre-shuffling of data based on some ID. Now, let's say if you have a table, say student, and you can bucket it on student ID. You cannot have partitioning on student ID because then what will end up happening is that you have like gazillions of partitions inside the table because you cannot like create a partition per user ID unless you have say like hundreds of users. And whenever we do partitioning, we try to keep the number of partitions like less than 100. Otherwise, it doesn't work well for us. And the reason is that, say if there's a executor which is writing out this partition data, now on the executor side, you need to have writers for each one of the partitions. And let's say if you have like thousands of partitions, then you'll have thousands of writers. And each writer has its buffer. And it turns out that it and it's not that stable. So keep the number of partitions less than 100.
Okay, so in the first few slides, there were like 3 types of joins that were mentioned. I'm wondering why you chose sort merge join versus hash join, and if there were like what performance improvements there were.
Oh, so we definitely like using any hash-based join because it's much faster than sort merge join. But turns out that most of our tables are super large in size. So if you have to do, say, a broadcast join, one of the relation has to be small enough so that it fits in memory on all the executors. And if that's not the case, you cannot do a broadcast join. And same goes for shuffle hash join. In shuffle hash join, whenever you do shuffle, and then on the reducer side, you have to cache the shuffle outputs for one of the tables. And if that is big enough to not fit in memory, then you cannot do a broadcast hash join. It just zooms out.
Go ahead.
Hey Tejas, just want to check, what's your timeline to commit Spark 19256 to Jira to open source?
Sorry, what's the Jira about?
Spark 19256.
So
Hive, Jira to support Hive bucketing.
Oh, so that one. So my plan is to get it done in next coming months. So I'm waiting for one of the refactoring that is happening on the writer operator. So the Hive insert into Hive table operator, that is undergoing some refactoring. And so I'm waiting for that to finish, and after that I can continue with the contribution.
Thank you.
Any other questions? We'll give a big hand to Facebook and Tejas for making valuable contributions to open source. And thank you.